Can you see the screen?
Yes.
Hello.
Yes.
Okay. So that was the multi-stage differential amplifier that we introduced in our last class. So we wanted to achieve high input resistance and at the same time high voltage gain. So in order to achieve high input resistance, called RID1, so we introduced this emitter resistance in the first differential amplifier, and we also took a lower value for the current I1 so that we get high value for R pi. So overall that will increase our input resistance RID1. So since the current is low, also we have emitter resistance that will reduce the gain and we will end up with low gain. And then in order to increase the gain, we add this second stage where we have taken high value of the bias current and also without any resistance. So in the emitter, so because both of these will result in higher gain for the second stage. So overall we'll achieve high gain at the same time high input resistance. And we are taking the output from the second collector, the single-ended output. So that is our the differential multi-stage differential amplifier that we discussed in detail in our last class, and also discuss some of the balancing issues. So first I'll go through that again, just the gain part. What was the overall gain for this differential amplifier? So overall gain, okay, I have to, the part is missing. So that was the output for the first stage that goes as the input for the second stage. And that was the differential input resistance for the second stage. Remember the connection, how it is connected, this side, since this side is plus, so that goes into Q3 plus sign, and the minus goes to Q4. So that is how we connect. Now the overall gain for this the output by input, VID, and we split it up as the product of two gains. The gain for the output is V0 by VOD, and then VOD by VID, that is the gain for the first stage. Now the second stage, we are taking the output from a single node. So for the second stage, the gain will be just half GM, and this is GM2 for the second stage, and RC2. So that is the gain when we take the output gain of the differential amplifier, when we take the output from a single node. For the first stage, that is, we are taking the output differentially, and also we have resistance in the emitter. So for this case, when we have resistance in the emitter, the formula is the resistance in the collector, so divided by resistance in the emitter. So we have resistance in the collector is RC1, and that is not the only resistance in the collector because the output is connected to the input of the second stage. So the input resistance RID2 will be like a load resistance for the first stage. And whenever we have a load connected to the output, so that comes in parallel with the collector resistance. So the effective collector resistance will be RC1 in parallel with RID2, but it will be half of that because half will go to other RC, and that divided by the emitter distance, which we have RE1 and small RE1 and capital RE1. So that will be our total gain expression for this. Now here in the last class we calculated all the parameters what we have in this expression, starting with the GM2. GM2 will be the IC2 by VT. Here IC2 is the current DC bias current that flows into the second stage, that will be half of this. So that we write as I2 divided by 2 VT. And what we calculated last class, that was 40 milliampere per volt. And then we also calculated the small RE1. RE is the, VT by IE. VT by IE1. IE1 again, the emitter current that is flowing here, which will be half of this bias current. So that will be, if we take that, that will be 2 I1. Just I1. So 2 VT by I1 is divided by. And that was 100 ohm, right? And RE1 given 400 ohms. And then we need another parameter, RID2. And RID2 is 2R pi. And given this value of that is I, so that way we write as 2 beta plus 1 RE2. And probably that's come out about 5K. So putting all the values of all these parameters here, RC2 is 3K, so that will be your about 60, or if you just want to put this times 40 times 3K, and that times RC1 is 20 in parallel 2.5, and that will be, we have here 100 plus 400, right? So that is all. And doing the math, you get 60 times famous 4.4. So 240. So it's probably about something like this. So that was our overall gain for this multi-stage this differential amplifier. And RID1 also we calculated. RID1 was about that will be, we have beta plus 2, beta plus 1, and small RE plus capital R. So applying the resistance reflection rule here, if beta is 100, so 201 times, that is 500, right? So that will be in ohm. If you convert into kilo ohm, that will be about 101 kilo. So we get almost about 100K of input resistance and also gain of 264, right? So 100K is quite high. Now that is all looks good here. Now let's consider a situation. Now this is without the output stage. We don't have any load connected here. Now what happens if you connect a load here? That is a gain, no load gain, right? Without any load connected. you have a load here, RL connected. Right? Load can have any resistance, that depends on the load. And some load can have low resistance, some kind of high resistance, we don't know that. Okay. So let's assume that it has a resistance of 1K. So what happens in that case? How the gain of the, then it will affect the gain of the first stage, because the load resistance will come in parallel with the RC2, right? So what happens, the gain of the first stage, sorry, the second stage. So let's say we call it 82, the gain of the second stage, which is V naught divided by VOD. So that will be half GM2. Now we don't, now it's not just RC2 that will come in parallel with RL. Right? So what we have RC in parallel with RL. So we have half, and GM is 40. Now here we have RC is 3K and RL is 1K. Right. So now if you take parallel combination, what will be the parallel combination? Can someone tell me?
So what was the question?
Sorry?
Can you repeat the question once again, sir?
Uh,
Parallel.
what is the value for this parallel combination? 3 and 1.
So 0.75.
How much?
So 0.75.
0.75. Okay. 0.75. So before it was 3, now it has come down below 1, right? There is a 0.75. So if you do the math now, you get here, it will be 30, 15. Did I get it right? Is it 15? 15, right?
Yes, sir.
So it's very low, right? So there's a drastic reduction in the gain from 264 to just 15, right? When you connect the load. So that is disastrous. Right? So how we overcome this problem? What is the way to overcome this problem? This is the loading effect now. So how do we overcome this problem? No idea.
So buffer.
Yeah, exactly. So we need to use a buffer to isolate the load from the output stage. So instead of connecting it directly to the output, so what we do, we put a buffer here. And buffer is nothing but a common emitter, sorry, common collector configuration. This is VCC. No, here will be low, but we need to put a biasing current here. So that we do like this to bias the transistor. Let's call it I3. And then we connect the load here. And we are taking the output from here. So that is our Q5. Is that clear, guys?
Yes, sir.
Now, what is the gain, right? When you after we connect the buffer, so what will be the gain? In order to find the gain, so now see what comes in parallel with RC. Before we had RL in parallel with RC. Now this RL is isolated from this RC by this voltage buffer. So RC doesn't see RL, but it sees what comes at the input of Q5. So let's say that is Ri3, the third stage. So what's the input resistance here? So that will come in parallel with RC2, right? So now here, instead of RL, we will have Ri3. So then in order to find the gain, we need to determine first what is Ri3. So what is Ri3? So Ri3, we can write applying the resistance reflection rule, nothing but beta plus 1 RL. Now assuming beta is 100, so 101 times 1, so we get 101 kilo, right? So we get a quite high gain, high input resistance for Q5 that will come in parallel with RC2. So now parallel combination RC2 will have in parallel with Ri3, and that will be 3 in parallel with 100, 101. Now how much is this parallel combination? Hello.
Yes, sir. 1 minute, sir.
Hmm?
2.30.
How much?
2.30.
2.30. Are you sure? Shouldn't be that low. Huh?
স্যার আমি আবার একটু করছি স্যার, আমার মোবাইল দিয়ে করছি, আবার একটু করে বলছি।
Okay.
So it's quite a bit around 3, sir.
Yeah, it should be around 3.
Yes, so 2.91.
2.91. Okay, so overall, I mean, the resistance, the collector resistance, there's a little change, little reduction. So overall gain will be reduced by little margin. So here we have 40 and then times we have 2.91. So that will be probably about 5.8, about 58, 3, 20, 40. So that will be about 58, right? So that will be the gain for our second stage. And before it was 60, now we have got about 58, so very close, little reduction. But that is not the overall gain, because now we have also you have to include the gain of the third stage. We have 3 stages. One is this, you can call it our input stage, and then this middle stage, that is our gain stage, to increase the gain. And then we have this third stage that we can call it the output stage. And that is output stage, we have to minimize the loss, right? Because of the low load resistance. At the input stage, we try to minimize the loss, have high input resistance loss that we might have because of the source resistance. If we have a source at the input side, something like this, when you connect a source, RS, and then you have the source voltage here, VS. So that is how you connect differential amplifier. The source, usually if differential amplifier take the difference, so source will have ground, so probably this will go to ground. So then basically this is how it is connected. So this terminal is connected, the positive terminal is connected to this side, and negative is grounded, and that means also you ground this part, so you don't need to actually connect here, because they both goes to ground. So that is how it will be connected. Now the VID will not be exactly VS, but there will be some loss here in the source relationship. So VID will be less than VS, and you can calculate VID like this, that VID will be VS times this RID1 divided by RS plus RID1. So that will be our VID, which will be less than VS. And that depends also on the input resistance, how less it will be. The lower is RID, the lower will be your VID. So the loss will be greater if your input resistance is low. So that's why we try to increase the input resistance, try to have as high as possible input resistance, so that will minimize the loss. In ideal case, if RID is infinite, right, so then the PID will be exactly equal to PS. So that is an ideal case, and that's why we said that ideal amplifier should have infinite input resistance. And that is how we minimize the loss at the input side by having very high input resistance. So that's the purpose of the input stage. And then when you increase the input resistance, gain goes down. So we add this stage, intermediate stage, to increase the gain. And then at the output stage, because when you connect the load affects the overall gain, reduces the gain. So introduce the buffer, voltage buffer, to minimize the loss at the output side. So now the overall gain will be product of the three gains. So here, overall gain, you have V0 by VID. We have here, let's call it the voltage here, V01. So V0 by V01. And this is the gain for the intermediate V01 by VOD. So these are the gain for these two stages. And with that, you have to multiply the gain of the this voltage buffer will be V0 by V01. Right? So that will be your overall gain. So you need to consider also what is the gain for this second, third stage, the voltage buffer. And that is this common collector. And common collector, we know the gain will be V01, sorry, V0 by V01. So the common collector is the resistance we have, the load resistance RL. There will be total resistance in the emitter RE1, sorry, we call it RE3 plus RL. So now it depends on RE3. So if RL is in the kilo ohms range, RE3 is usually in the ohms range. So it's very small. So VT by I3, right? VT by I3. It depends on I3. If I3 is 1 milliampere, then that will be about 25. Someone is waiting there. This is the problem. Do it again for this guy. Okay, guys, any question? So far? Now this one has one problem here. That is, you see that we are able to overcome the problem of the load resistance. Now the problem here is the DC bias voltage. You have the V01 here. Sorry, the DC bias voltage. What's the problem? DC bias voltage. In the last class, we calculated the different DC bias voltages. Here we have the current I2 flowing, that is 2 milliampere, and half of this current will flow into each of these emitters. Here we have 1 milliampere. Now, so 1 milliampere will be flowing here. So also the current here IC is alpha I. If alpha is close to 1, so this will be also approximately 1. So the voltage drop that you will have here will be about 3 volt. Right? So that I lost that part anyway because of that guy. Okay, so the voltage drop that we will have here is about 3 volt drop will be here because this is 3K. So it's 15 minus 3. The voltage that comes here will be 12 volt. So you will have 12 volt coming at the base of this. So then you have 0.7 volt drop here. And then you get a voltage of 111.3 volt. So that is in addition to the output voltage V naught. That's a small signal voltage V naught we are considering. And that is a DC voltage, right? And DC voltage this due to the biasing voltage, right? In conventional amplifier, right? So what we do, we use a coupling capacitor to block this DC voltage coming to the output or coming to the load. Right? We use a DC blocking capacitor. But in integrated circuit, the capacitors are not used. They are, every attempt is made to avoid the use of the capacitors because capacitors are bulky, they are big in size, right? They can take lots of space. But integrated circuit, the idea is to minimize the space, right? Make things as small as possible. So the use of the capacitors is not actually compatible with the philosophy of the integrated circuits, while everything is tried to squeeze and make as small as possible. So how we can avoid this DC bias voltage coming at the load, because this will cause a very large current flowing into the load, and it might damage your load, or if it doesn't damage, it will at least you will have a lots of power drain and a power loss, and your circuit efficiency will go down, and it will generate heat. Obviously, your performance will degrade. So many other issues, right? You will have because of the high this DC voltage appearing at the load. Now, how to avoid all that? So, basic idea is to, if you can make the voltage, this voltage here 0, right? VDC, the DC voltage coming at the output of the amplifier, should try to make it 0. Right? If you can make the DC voltage appearing at the output to 0, then you will have only the AC voltage. You will not have the DC voltage, right? So that will solve your problem. Now, how we can achieve that, right? So that is the second question. Is that clear, guys? Do you understand what is the problem we're talking about?
Yes, sir.
Okay, so that is important. Unless you understand what is the problem, so you will not have any clue what the discussion that will follow. So now, how do we solve that problem? Okay. So we will focus on the output side. I will not be drawing the whole circuit because that will just occupy the whole space and not have any space to write. So let's focus on the circuit, the output side. So I draw the here from the Q4, so you have just can connect later on what we are doing. So that is, we have RC2 here. We have I2, and that is our Q3, Q4. What we do, we take the output from here. Oh my gosh. This we call Q5. And then take the output from here. That is our RE, the emitter side, RE3. And that's collector RC3. Now, then we have the output from here. We use another transistor. So that is our Q6. So that is our I3. And we connect the load here, RL. So that is our class VCC. Also class VCC, and that is our 15. Okay. So now here, what we have shown that we get a DC bias voltage of 12 volt. Right? 12 volt here. And okay. Now this is the circuit that is used to shift the voltage level. So this is called this circuit is called the DC voltage level shifter. This circuit is connected here to shift the DC voltage level so that at the output, the DC voltage is 0, right? At the output, DC voltage should be 0. So that is our main target. So now if voltage here is 0, you see that you will have 0.7 volt drop here, plus minus. And it was biasing voltage for bias voltage for the base emitter junction here. And if you have a 0.7 voltage drop, then voltage here will be 0.7. Right? Voltage here should be 0.7. So now this circuit should be such that you have a 0.7 volt here, DC voltage. Then the output will be 0 volt, right? If you have 0 here, then output will be minus 0.7. That's not what we want. We want output to be 0. And if voltage at the output DC voltage is 0, then voltage here should be 0.7. So now our target is to make this voltage 0.7. Now, how do we achieve that? So this is going to the other supply voltage. You see that op-amp how it is connected. You have plus VCC minus VCC, right? Plus supply voltage, negative supply voltage. So voltage at this end, if you call it VEE minus VEE, and that should be then minus 15, right? Something like you have plus 15 minus 15. So say minus 15 volt here, right? So then there should be some current flowing here. This is our direction of the current because this is IE, how the transistor connected. So this is a PNP transistor. So the current is flowing in this direction. There is I3. So you have I3 flowing in this direction. That will be IC, right? IC3. Now our main target here is to make this 0.7. That will depend on this voltage drop here, right? So this is our and the collector terminal for the Q5. We can call VC5, right? So VC5, what should be the voltage VC5? So that we can write VC5 should be minus 15 plus. Then you have the voltage drop here. Okay, let's get rid of that. So we have the voltage drop here, that is IC3 RC3, right? And IC3 is flowing in this direction. So minus 15 plus this voltage IC3 RC3, right? And that total should be 0.7 volt, right? The total voltage here, VC5, that is 0.7. So from this, we have to come up with suitable values for IC3 and RC3, right? So there are two variables. So we need to fix one and then we can determine the value for other. So if we assume that, let's say IC3 we take as 1 milliampere. So then what should be the value for RC3? Then we can do the back calculation here. So RC3 will be 15 goes to the other side and we have 15.7 divided by IC3 is 1 milliampere, and that will be gives us 15.7. Okay. So that's the value we come up for the RC3, assuming that IC3 is 1 milliampere. Is that clear, guys?
Yes, sir.
Okay. If you have any questions, let me know. So that's how we can fix the voltage to be 0.7 here. And so that is fixed. Now we have assumed that IC3 is 1 milliampere. Now you have to ensure that it is 1 milliampere. How do you do that? How do you ensure the value for IC3, right? So for that, we have to go to the emitter side of this transistor and see, how IC3, right, is related to that, or how we can fix IC3, right, by designing the emitter side. The collector current IC is alpha I, right? Alpha I. So to simplify the calculation, assume that alpha is close to 1. So then we just write IC is IE, right? So IE should be also 1 milliampere. If this is 1, then we will have about 1 milliampere here. And then you see that because of this IE, there will be voltage drop here. That is IE3 and RE3. Okay? Now you see that the voltage here is 12 volt because of this circuit that we have before this Q5. The voltage is fixed at 12. And this is the PN junction again. So you have a 0.7 volt drop here, right? Plus minus. So voltage, that is our here, that is VE5. VE5, how much VE5 will be?
So VCC minus I1.
No, the magnitude. The charge surface coming later. VE5 will be how much? How much will be the magnitude?
Sir, what is the value of RE3?
No. RE3 value, first you need to find VE5, then you can determine RE5. How much VE5 should be?
So
Like
50.
here, VC5 is 0.7, right?
Yes, sir.
So like that, how much it should be VE5?
Okay. So it should be greater than 12.
How much greater? You have to come up with the exact value, no?
Sir,
How much greater?
sir,
Yeah.
greater so that the output voltage can swing.
Now look at the circuit and try to come up with the value. You're thinking too much. It's all here. So you have 12 volt here at the base. Now there's a 0.7 voltage drop in the base emitter junction, right?
Yes,
So,
sir.
so how much will be V voltage at this point?
Sir, 11.3.
11.3 will be, it will be below this base voltage.
No, sir. Sir, then 15 minus IE3 RE3.
And how much is that?
So we need to determine RE3.
And how do you do that?
So minus RE3.
That's very simple. It's 12.7.
Yes, sir. It is. Yes, sir.
Does it make sense?
Yes, sir.
So why couldn't you say this? Why it is so long? This is pretty time. That's the problem. Not so voltage here is 12 volt and you have 0.7 volt. This is positive on this side. This voltage up. No? You're going up. It's not going down. So voltage here is higher than you said. That voltage here should be greater than this, right? And how much greater by the forward bias voltage of this PN junction? 0.7. So voltage here is 12.7 volt, right? So that is our V5. And if you write from the this, from the supply voltage, if you track the voltage from VCC, so that will be VCC minus I3, IE3, RE3, right? So that will be the, if you are tracking from here, and then the field voltage here at this point. So now from that IE3 we have already determined that should be 1 milliampere. So then we can have an estimate for RE3 that will be we have 12.7. We will change the sign, so that will be VCC minus 12.7 divided by IE3, right? So you have, if you take this VCC 15, you get 2.3, you get 1 milli, and that gives you 2.3 K. Right? So that is how you determine the different values. That will be 2.3 K, and here you will have 15.7 K. Right? So if you take these values, right? So this 2.3 K will ensure that the 1 milliampere current will flow here. IE3 will be 1 milli, and then the same 1 milli will flow in the IC3, and we have taken this 15.7 volt here. So the voltage drop here will be 15.7 volt. So minus 15.7, and then you are going up by plus minus 15 and plus 15.7 will give you a 0.7 volt drop, 0.7 volt, right, at this node of collector BC5. and then 0.7 drop here to make it 0. Is that clear, guys? Any question?
Clear, sir.
So that will be your complete circuit here. But you know that as you introduce more and more components, your circuit gets bigger and your calculation gets larger, and more components are introduced. You have introduced another component here. So now the gain, overall gain will be gain of the 4 stages. Now you have 4 stages. At the input stage, this gain stage, DC voltage level shifter, and then this common collector, the voltage buffer at the output, right? So if you write the overall gain, that will be V naught by VID that we had at the input. So we assign the different voltages. Let's say this is V01 and this is V02. So then you can write V0 by V01, V01 by V02, and then V02 by V0 VOD, and VOD by VID. So that's the overall gain, and we have already addressed these 3, right? The voltage buffer. This one is the gain stage, and this is the input stage. So this we have. So in addition, we get this extra term, right? And that is because of this voltage level shifter. What is the gain of this voltage level shifter? No idea. This is we have introduced to shift the DC voltage level, but any transistor like also is an amplifier, right? So it will add some gain, right, to the circuit. How much gain it will add, right? So how do you determine the gain? So first look at the circuit and find what is the amplifier configuration here.
So common emitter, common collector.
No, just the voltage level shifter. What is the voltage level shifter? What is the amplifier configuration? Q5.
Sir, cascade configuration.
I'm talking just the Q5.
Sorry, sir.
What is the amplifier configuration of Q5?
Sir, common emitter
Just common emitter.
with RE, sir. Common emitter with RE.
Common emitter with emitter resistance. So what is the gain expression for that?
Sir, the resistances in the collector divided by the resistance in the emitters.
Right. So the gain expression for the common emitter with resistance in the emitter, here the voltage here we call it V01. So that's the gain for the third stage. Sorry, yeah, third stage. We can write as 83. That is V01 divided by V02. There's the resistance collector, resistance emitter with a minus sign. This common emitter gain is always negative. So RC, the resistance in the collector. What's the resistance in the collector now, right? Now we have RC3. Now since this is connected to the input of the Q6, so the input resistance of that will come in parallel with RC3. So we have RC3 in parallel with RI input resistance of the transistor 6 divided by the total resistance in the emitter. So that will be RE3 plus capital RE3. So that will be the gain for the DC voltage level shifter, and RI6, you just apply the resistance reflection rule, that is beta plus 1 R, right? So that will be your RI6. So that will be the gain that will be introduced by this DC voltage level shifter. And we'll have some modification of the gain here. Now, since that output goes to the input of the Q5, so the input resistance of Q5 will come in parallel with RC2, if you call it RI3. So then the gain of the second stage AD2 will be half GM2 times the RC2. Now the RC2 will be in parallel with RI3, right? And RI3 will be beta plus 1 times RE3, right? Any question, guys?
No, sir.
Okay, so that is the overall gain for this amplifier. The other parameters here that might be of interest here, input resistance, we have already addressed what is the input resistance. And the other part is the output resistance, that we look from the load side, R or not, right? So what will be the output resistance here? What will be the output resistance?
Sir, infinite.
How it will be infinite?
Sir, because of the resistance of the current source.
Yeah, that is infinite because okay, but that is infinite. But then you make the current source open, right? If you make it open, then still it is connected to something, right?
Yes, sir.
So shouldn't you consider that?
No, sir.
No. Why not? Something in parallel with infinite, it becomes infinite. Hmm?
Sorry, sir, I couldn't hear you properly.
You said I said that this is connected to the emitter, right? So
Yes,
even
sir.
if you make this one open, because you said this is infinite, make this one open.
Yes, sir.
So this is still connected to something, and there will be some resistance there. So won't that affect, or won't that have any contribution to the output resistance?
Hmm. Source open. Sir, I think there will be no effect.
Why? Why
Because
not?
this is open and not connected to the circuit then.
Yeah, I make it open. This is open, right?
Yes, sir.
Current source is open. This current source is open, but this part is connected. No?
Yes, sir.
So your output resistance will be infinite still.
No, sir. RE6 will be there.
So there is the question. And what will be the output resistance then? It is not infinite. Only the current source part is infinite, but we have resistance coming from that.
Yes,
Right?
sir.
We need to consider that we have a small RE3 and that plus, what will be the plus additional term? What is the resistance in the base? So that is the resistance that you can see from here. Let's call it RO prime. Right? So if that is the RO prime, that will be reflected into the emitter, and you write like this: RO prime divided by beta plus 1, resistance reflection rule. Now the question is, what is RO prime, right?
Sir, RL by beta plus 1?
Hmm?
Sir, RL by beta plus 1?
RO by beta plus 1. Oh my gosh. If you look towards the base, then it will be RL divided by beta plus 1. I mean, it depends which way you are looking, you know. You're looking away, right, from the base. You're not looking into the base, right? So looking away on the towards the other side of the base, right? So you have to see what you have here, not on this side, right? So what you have here?
Sir, the output resistance like the common base.
Common base. What is common base?
Sir, 1 minute.
You have RC3 here, no? Between this point
Yes, sir.
with this point, and this is a DC source, and ideal this is zero resistance. So if you think about the resistance, actually this is the resistance is zero, so that goes to ground. So between this point and ground, you have RC3. So R naught prime basically will be RC3. There is other part of resistance that is looking into the collector. Looking into the collector, that you see the output resistance of the transistor, and that will be very high because the common emitter with the emitter resistance has a very high output resistance, and that is given as the RO for common emitter with emitter resistance RE. So that is the small r naught times 1 plus GM. If you remember this, right? R pi in parallel with RE. So that's very high, and if you that will come in parallel with this. So that will make your, I mean, almost equal to RC3 because obviously this will be much smaller than this. So we can ignore this part and just write that output that is seen from this side. Looking into the collector of Q5 will be just RC3. So R naught will be just RC3, and you can just write RE plus RC3 divided by beta plus 1. So that will be the output resistance. Any question, guys?
No, sir.
Hello. Walaikum Assalam. Alhamdulillah, covered. Usually there are different steps, other than that. अच्छा তাহলে হ্যাঁ হুম 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 আচ্ছা হ্যাঁ 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 মিসিং হয়ে যাবে আর কি ইন জেনারেল দিয়ে দেন হ্যাঁ হ্যাঁ হুম 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 আচ্ছা আচ্ছা ঠিক আছে so is that understood?
Yes, sir.
Okay, any question? So we have addressed the different aspects of this multi-stage differential amplifier. What are the issues and how we can overcome, solve those problems. And that is I3. So voltage issues that, so that you have your bias voltage can support the signal voltages, right? And how to address that. And the other part remaining here, that is the bias current. How do you choose the bias current? We have mentioned right in our discussion that we take low value for this bias current to have high input resistance. If you take a low bias current, that will give you high value for RE, because RE is weekly by half of this, right? RE. So low value will give you high value for RE, and that will give you a high value for the input resistance. And if you want to have a high gain, then you take high value for current, because that will give you a high value for GM. GM is IC by VT, right? Which is actually half of I divided by VT. So you get high GM and you get high gain, right? So if you want low gain, low out, high gain, you take high value of this bias current. If you want high input resistance, you take low value for the bias current. You adjust them accordingly, so you get your desired value. And there is another aspect, another point you need to consider when you take the bias current, especially in the output side, because output side, the current that will flow into the load usually high, right? It depends on the load how much current it demands, right? So that will also affect the bias current will also depend on how much current it has to supply. In any case, this bias current, is talking about the output side, I3 has to be larger than your, at least equal to the maximum value of the I naught, because I naught will flow like this. If we consider this an AC signal current, so it has a minimum value, maximum value, right? So that is I naught max. So the I3 that you choose here has to be at least equal to or greater than I naught max. Let's say, and so first you have to determine what is the maximum value of I naught max. So that depends what is the maximum value of the voltage that your load will have, or that your amplifier will produce. Let's say your V naught is maximum V naught is, sorry, let's have some space here. let's say that okay, we need to find I naught max is how much. So it depends on V naught max, how much is the maximum voltage. If your V naught max is, let's say, 5 volt, and your RL is load is 1K, then I naught max will be V naught max divided by RL, and V naught max is 5 volt, and that is 1K, so it will be 5 milliampere. So what we see that your I3 has to be greater than or equal to 5 milliampere. It has to be at least 5 milliampere. Otherwise, it will not be able to supply the required load current, right? So bias current has to be at least equal to or greater than the current that the load demands, right? Otherwise, it will not be able to supply that current and it will go into cutoff mode. Like the op amp, they are designed to supply maximum 20 milliampere of current. So the bias current that is set inside the op amp, the circuit that is designed, it supplies the op amp with 20 milliampere bias current. So you cannot have more than 20 milliampere current in the load. Even if the load demands more, it will not get that current, it will just go into cutoff. And it will, yeah, output will get truncated. Is that clear, guys? So we'll talk more about this issue of this current issue and how we can modify the circuit to accommodate higher currents and address those issues in our next lecture. Guys, any question?